Hello everybody again and welcome back to the second part of the path planning unit. In this case it's more related to the obstacle avoidance. Okay, so just to summarize, in the previous part, in the part 1 of path planning, we saw that you can send goals to the move base node, and then this node sends this goal to the global planner, which calculates a safe path to reach that goal using the global Cosmap. Okay, and then we saw that you have different kinds of global planners, that each one has its own specifications and way of working. Yes. Then there is one thing there that we skipped in the previous chapter. That is when the global plan receives the goal and calculates the trajectory, the global trajectory, let's say, it then sends this trajectory to a local planner. Yes? So once it calculates its path, the global path based on the static map, it sends this path to the local planner. Yes? Then this local planner will execute each segment of the global plan. Let's imagine the local plan as a smaller part of the global plan. Yes? So basically, this local planner, given a plan to follow, which is provided by the global planner, the local planner will provide velocity commands in order to move the robot. Okay? So basically, the global plan, when it calculates its path, it sends this path to the local planner, which divides this plan in smaller parts and executes each of these parts. Okay? And for executing these parts, obviously, what it does is to generate velocity commands and send them to the robot so that the robot moves and starts following the path. Okay? Then, as I've already told you before, unlike the global planner, the local planner does monitor the sensors data, in this case the odometry and the laser data. Yes? And chooses a collision-free local plan. Let's imagine this local plan as a smaller part of the global plan. Okay, you will see now better with an exercise. Okay? So basically the important thing here is that the local planner is able to recompute the robot's path on the fly. So basically, this local planner receives a global plan to follow, and then it divides it in smaller parts and it starts executing each part of this plan. Yeah? But if some kind of object comes across and puts itself in the middle of this plan, it can recompute the path in order to avoid it. Yes? The local plan can do this, can recompute the path on the fly. The global planner cannot do this. The global planner just creates a static plan, yeah, based on a static map, because it doesn't take into account the sensor readings, but the local planner does take into account sensor readings. Okay, that's why it's able to recompute the path on the fly depending on the new things that appear in the environment. Okay? And then, it publishes this local plan into two topics, into the local plan and also into the global plan. Into the local plan, it attempts, it publishes the smaller plan, let's say the local plan itself, and into the global plan it publishes the section, the portion of the global plan that it's attempting to follow. Yes, this is published into the global plan. But well, let's stop the talking and let's do one exercise in order to be able to visualize this a little bit better. So basically, let's launch our navigation system. Okay, actually, I can launch mine. So ROS launch my move space launcher, and the one, there we are. And let's also open an Rviz window. There we are. Let's then open a graphical interface window here in order to be able to visualize Rviz. There we have it. Okay, so here we have the navigation system up and running. So first of all, let's localize the robot. Okay. More or less it's around, let's say, here. Okay, there we are. And then here I have configured the global plan. Yes. The nav FEN ROS, which is the global planner. But now I'm going to duplicate this plan element, and I'm going to configure it for listening to another topic, which is going to be this one, the local plan. Okay? As you can see here, the DWA, which is the local planner, has the global plan and the local plan. Yeah? As we've discussed right here. Okay? But in this case, I'm going to select the local plan. So I want to visualize the local plan. There we are. Excellent. So now let me take out this pose array. And then let's come here closer to the simulation in order to be able to visualize it properly. Let's come here, closer. Okay, so now I'm going to send a goal to the move base node so that the global planner will calculate its path and it will be published here. Let's put the global plan in, let's say, green. Okay, so that the global plan will be printed in green and a local plan will be printed in pink. Okay, so let's send a goal around here. And as you can see, the global plan is here printed in green, but I have also a smaller plan which is in pink. Yes, and this is the local plan. Yeah, so the local plan keeps, yeah, it's like it divides the global plan in smaller parts and it keeps executing these smaller portions of the plan. Yeah, let's see if this reaches the goal. Yeah, so there you had a visual way of seeing this. Yeah, so we have the global plan, which is the big plan, the whole plan in order to arrive from the point A to the point B. Yes, and then this plan is divided into smaller parts by the local planner and then executed. That's why the local plan was a small arrow compared with the global plan. Yes? Here it's trying to set the correct orientation. Okay, this can be configured so that it doesn't have to be that much precise. We will see this later in this. Yeah, there it is. Go Richard. We will see how we can tune this behavior later in this chapter. And let's just send another one here just to visualize it again. And here we have in green the global plan. Yeah, and there we have in pink, yes, the local plan. There it is. Okay. Excellent. So yeah, let's continue with our explanation. So the same happens with the local planner than with the global planner. You have different planners, okay? For instance, one is the base local planner, another one is the DWA local planner, Another one is the event local planner, the tip local planner. You have different local planners, and each one has its own way of working, its own specifications, okay? Down here, you can check information about each one of them, how they work, etc. But for now, let's just have a look at this base local planner, which is the common way of how a local planner works, okay, step by step. So basically, the basic idea of how a local planner works is, first, it does a sample from the robot's control space. Yes? Discretely sample from the robot's control space. Okay? Then, for each sampled velocity, it performs forward simulation from the robot's current state to predict what would happen if the sampled velocity was applied. Okay? So basically, it does let's say, simulations of different velocities, and it simulates what would happen if each of that velocities was applied to the robot. Would the robot collide with something? Everything would be fine. Yeah. So basically, it does different kind of simulations, applying different velocities commands to the robot. Okay. Then it evaluates each trajectory. So each of these simulations, it's evaluated. Then it discards the illegal trajectory, so for instance the ones that would collide with something, and then it picks the highest scoring trajectory and sends those velocity commands to the robot. Yeah? So basically, let's imagine it says, okay, it does a simulation applying some velocity commands so that the robot would go like this, okay? And the other one, it's like this, okay? So then it would evaluate and it will find this first trajectory illegal because it would hit the wall. And the other one would have then a highest scoring. So then it will execute that one, okay? So this is basically the behavior, but with more simulations, not just two simulated movements, okay? And then rinse and repeat. So basically, this is the workflow of the local planner, okay? Then the most used one, the most commonly used, is this WA local planner, okay? And this is actually, I think it's the one we are using in our system. Let me see. Yeah, here we have it. The DWA planner ROS. Okay, so this is the most used local planner. And as we saw for the global planner, you can change it. You can set different local planners. You have here how to set them. And then here you have a small exercise in order to modify the local planner for another one and test the differences, how they work, etc. Okay? And obviously, the local planner has also parameters, has its own parameters, which can be divided in subgroups. For instance, first we have the robot configuration parameters. Yeah, you have them here. I'm not going to analyze them one by one now. You can do that when you do the course, read and see what each of them does, okay? But these are the robot configuration parameters with acceleration limits, velocity limits, etc. Okay? Then we have the goal tolerance parameters, which basically sets which tolerances has to have the goal. So for instance, the yaw goal tolerance is the tolerance in radians for the controller in yaw rotation when achieving its goal. Do you get this? So for instance, when you see that the robot reaches the goal but it keeps turning around, rotating, this is that it's trying to find the exact orientation of the goal that you have set for the robot. Yes? And this can be tuned with this parameter. So if you put a higher tolerance, the robot probably won't keep rotating like we saw it happened before, yeah? And if you put a smaller tolerance, then the robot will try to be as much precise as possible, so it's possible that you get your robot rotating, trying to find the exact orientation, even when it reaches the goal, yeah? Then you have also the XY goal tolerance, different tolerances for the goal. For instance, you have here an exercise to modify the XY goal tolerance. What this means, for instance, with a high XY tolerance, for a, let's make this, okay. Okay, there we are. So for instance, for a high XY tolerance, for a high value in this XY goal tolerance parameter, being the goal, this point here at the end of these arrows, being the goal here, even if the robot is here, this could be accepted as a goal reached. Yes, because the XY tolerance is very high. Yeah, so even if the robot is far away from the goal, it could be accepted as a good as a goal reach. Yes. With a low XY tolerance, this doesn't happen. So the robot has to be actually in the goal, in the real position of the goal to be accepted as a goal reached. Yeah? For instance, this is the... Let's make this smaller again, yeah? Okay, there we are. This is what the XY goal tolerance does. Okay, so yeah, here you have an exercise to test this. Then we have here more parameters, the forward simulation parameters, how much time you want your robot to simulate. For instance, you can have a look at this more slowly at your pace on your own. Then here you have an exercise to tune this sim time parameter and see how it affects. And basically, as you can see, with a regular sim time, the local plan arrow is quite short, and with a high sim time, this local plan is much larger because it is simulating more time. Yeah, so the local plan it's larger. Yeah, well, basically you can test this. You have this exercise here. And then finally you have also some trajectory scoring parameters. All these are parameters in order to tune how the local planner works. Yes, here you have an example of the parameters of a DWA planner ROS. Set it here. Yeah, this is an example configuration file for a local planner. Yet here you have another exercise in order to tune this path distance vs parameter. Okay, but well, I will leave you time to do these exercises at your pace. I will continue with the explanation. Okay, then again we have seen the global planner, the local planner now, and in the previous chapter you also saw the global Cosmap. So now it's time to see the local Costmap, okay? And the first thing you need to know related to the local Costmap is that the local planner uses the local Costmap in order to calculate its plans. So, as you've learned, the global planner uses the global Costmap. The local planner uses the local Costmap, okay? Then, the main difference, you already know this also from the previous chapter, the main difference is that unlike the global Costmap, the local Costmap is created directly from the robot's sensors readings. Okay? So it is actually sensing the real environment. It's not basically in some static map that you created before, yeah? It's actually creating the map from the live readings of the sensor, from what actually the robot, is viewing, is getting from the environment. Okay, so let's do a quick exercise here to better visualize this and get a better idea. So what we are going to do basically is let's put the robot here, for instance, looking in that direction. Okay, there we are. Okay, let me do one quick thing in order to clean this. There we are. Okay. Okay, so here we are. We have the global Cosmap, which is this one you visualize in black, and we have the local Cosmap, which is this one in color, which is what actually the robot is sensing, the laser is sensing, yeah, the readings of the laser. Then what I'm going to do is to add an object which is not in the static map, so in the global Cosmap, okay? Then for that I'm going to copy one URDF file to my workspace. I can do it with this command here. Let's execute this command here. And as you can see, a new URDF file appears here. And now I can execute this command down here in order to spawn this object into the simulation. You will see it will spawn around here. So let's execute this command. And you will see that a new object will spawn here in the simulation. There we have it, excellent. And then, okay, so as you can see, this object doesn't appear, yeah? The global pass in the global Cosmap is not there because that object is not in the static map we have used in order to create this global Cosmap, and in the local Cosmap is not either because the robot is not detecting this obstacle, yeah, because it's not looking into that direction. So what do you think it will happen when I face the robot in that direction so that it visualizes this obstacle? Let's try. Let's send a goal to the robot around here. Okay, for instance, here it's okay. So now the laser is starting to detect this object. There you have it. And this object is placed in the maps now. Yeah, it's first placed in the local Cosmap, and it's also placed in the global Cosmap. Okay, there you are. So now I am detecting this object because, yeah, the local Cosmap, as you can see, it's calculated from the laser readings. Okay, excellent. So yeah, basically this is the local Cosmap and how the local Cosmap works. There we have I have some screenshots here. Okay, so then as well we have some parameters for the local Cosmap. Here you have them. And here you have an exercise in order to tune some parameters for this local Cosmap. This is very similar to the exercise you did. You did almost the same for the global Cosmap. Yes. So now here you have to repeat the same in order to tune the parameters of the local Cosmap. So let's do this first part very quickly. So basically you will need to create a new file here for the local Cosmap. Let's add it here and copy this Cosmap local parameters file to your file. So cp Cosmap local to home user workspace src, my move base launcher params, and my local. Okay, so now here in the my local Cosmap params you have the parameters for the local Cosmap. Yeah, here you have them, and of course you will also need to modify here where this local Cosmap is being loaded, which is here. You will have to change this so that it gets your file and not the one that is installed in the system. Yeah. So here you would put the name of your package, which is my move base launcher. Then the directory, it's called params, and the file is my local cosmap params.yalm. There you are. Okay, so now you can modify the parameters you have in here, and you can test them, so you can proceed with this exercise. I will leave you do it for your own. Here, in this case, you are modifying the width and height parameters, which will make the local cosmap to be higher or smaller, yes. And then, yeah, basically for the local cosmap, you will use two layers, which are the obstacle layer and the inflation layer. As you can see here, you have the obstacle layer and the inflation layer. Yes. Then there is one important thing to note here, because compared with the global cosmap parameters, you had also here some layers. For instance, the inflation layer is used both in the global cosmap and in the local cosmap parameters, as you can see. Yes, this plugin is used in both. And the obstacle layer, yes, which is this one, it's used in the local cosmap and in the global cosmap as well, but as you can see, the plugin is different. Here we are using the voxel layer, yes, and for the local cosmap you will use the obstacle layer. Yes, there are some differences between them, but you need to take this into account, okay? For the obstacle layer, in the local cosmap you will use the obstacle layer, this one here, the cosmap to the obstacle layer, and for the global cosmap you would use the cosmap to the voxel layer, okay? And then we have this static layer in the global cosmap, which is obviously not used for the local cosmap, okay? Then, yeah, great. So, okay, I have some more parameters here in order to modify. So, for instance, one of the parameters of the local cosmap is this update frequency, which is the rate at which the local cosmap is updated with the new readings from the sensors. You can also modify here this parameter and test it. And then, okay, there we are. So as you can see, here we're specifying the type, which is actually the source code or the plugin that we are going to use. But here we have a name. And this name, what does this mean? Yes, this is basically a source code. But this, what is this? Inflation, obstacles, laser. Here also obstacles, laser, inflation, static. Okay, so this is basically the name of the plugin. And with this name, we can actually configure some things for these plugins, for these layers, okay? But this is neither done in the global cosmap parameters or in the local cosmap parameters. It's done in a different parameters file, which is the common cosmap parameters file. Yes? Here we have it, the common cosmap parameters file. That in this file, we basically define some parameters, which are the footprint of the robot radius, and the parameters for the layers. Okay? Then, each layer, the obstacle layer, the inflation layer, and the static layer, will have its own parameters that can be configured. Okay? You have them here. But this is a little bit confusing, so let's move to the exercise so that you can see this better. So first of all, let's create a new file for the common cosmap parameters. I'm going to create a new file here, name it my common cosmap params.yalm, and to this file I'm going to copy the contents of this cosmap common YAML file of the Husky navigation package. Okay, so cp cosmap common to home user catkin src params my common cosmap. There we are. Okay, so now I have filled this common cosmap parameters files, and here I have it. Okay, so as you can see here, I have some parameters like the footprint. I have also here a robot base frame, update frequency. Well, some parameters, and also some ranges for the obstacles. And here I have these names, the static, the obstacles laser, and the inflation. Yes, these are the names. Static, obstacles laser, inflation. Yes, and here obstacles laser and inflation. Yes, so basically here I have regular parameters, which are these ones, and then I have these namespaces of the layers, which inside contain its own parameters. For instance, the obstacle lasers layer contains information about the laser that this robot uses. So which type of message uses, which is laser scan, in which topic this is published, this information is published, which is the scan topic, okay? For instance, in the inflation layer, we specify the inflation radius, so how much the objects will be inflated from the static map. Yes? Okay, well, I think you can do this exercise by your own, read this carefully, and follow this exercise. Here you will have to modify the obstacle range parameter, which is this one here, as you can see, the obstacle range parameter. And what will this cause? Well, basically it is the range in which the Cosmap will display the obstacles. Yeah. So for instance, if you put an obstacle range of 1, which is a very low value, yeah, the local Cosmap will only display the obstacles when the robot goes really close to the obstacle. Yeah, that's this obstacle range parameter. Then from the inflation layer, for instance, you have also other parameters like the inflation radius. So here it tells you to customize, to tune this inflation radius parameter here. And basically what will change? With a low value, as you can see, the obstacles are inflated with a small area. Yes, as you can see, this blue area here. But if we put this value to a higher value, these obstacles will be much more inflated. Okay? And this blue zone means that the robot cannot pass through there. Yes, this is the limit where the robot can be, as you can see. Yes, so this is a very important value as well. And this will depend basically on the radius of your robot. Okay? So yeah, more parameters to tune here in the common Cosmap parameters file. And finally you have the static layer, which is this one here, okay, where the most important parameter is this map topic. So from what topic it can get the map. Yes? Excellent. So yes. Let's move on with explanations, and it's time to talk about the recovery behaviors. So basically, I'm going to try to do this most summarized possible. So basically, the recovery behaviors is when something goes wrong, these recovery behaviors will be activated in order to try to solve the problem by itself. Yes? And basically, so for instance, let's say the robot gets stuck at some place or whatever, then the recovery behaviors will be activated. And basically, the navigation system provides two recovery behaviors. One is the rotate recovery, which is that the robot starts to rotate on the z-axis to see if it can find a way to go out from there. Yes? To see if it can find a free path to move or whatever, okay? But basically it starts turning on the z-axis, rotating, yes, on its z-axis. And the other one is the clear Cosmaps. Yeah, here you have some parameters for this rotate recovery behavior. I will leave this to do it for your own, because this is more extra knowledge. It's not core of the navigation system. I think the most important parts we have more or less seen them quite well, which are the Cosmaps, the planners, the move base node. So yeah, here you have some more parameters for the rotate recovery parameters. And the other one is the clear Cosmap, which basically is to clear it clears the local Cosmap. It removes all the obstacles that appear in the local Cosmap, and it starts from zero, detecting. Yeah, this is because sometimes if there's people moving around, the local Cosmap can keep some obstacles that are not really there anymore. So for instance, now I am detecting this obstacle here, yes? And let's turn the robot and put it looking to another direction, for instance, there, so that it doesn't detect this obstacle anymore. Okay, as you can see now it's doing strange things. Okay, so let's give a go around here. Come on, there we are. Okay, so now it will be looking into that direction, so it won't detect anymore this obstacle here. But as you can see, the obstacle is kept here. Okay, it's not removed. Yeah, even though maybe the obstacle is not there anymore. So for instance, let me remove this. This is still there. Yes. So how can this be solved? Because maybe I want to plan here, and the planner will say, hey, you cannot plan here because there's an obstacle. But in the real world, the obstacle is not there anymore. But it is in the local Cosmap, yeah? But this can be, for instance, solved with a clear Cosmap. A rotate recovery behavior will start, the Cosmap will be cleared, and then this obstacle here will be cleared from the Cosmap. And this can also be done using the clear Cosmap service, which is this one here. So for instance, if I execute this command here, ROS service call of the move base clear Cosmaps, tap to complete the message, yeah? So here I have the obstacle, and if I execute this command here, let's execute it. As you can see, the Cosmap is cleared and the obstacle disappears from there, okay? This can be achieved as well with this service, okay? Here I have a small exercise in order to test this. This I have just done. Excellent. So let's move on. We have also here the oscillation suppression, which is some parameters that you can tune in order to avoid the robot to keep oscillating when reaching a goal. Yes. And yeah, here we have a recap, because between this unit and the previous one, Path Planning Part 1 and 2, there have been a lot of new concepts introduced. So here you have a recap in order to do a summary of everything you have learned in these two chapters. So for instance, the move-based node, the global planner, the local planner, the Cosmaps, recovery behaviors, configuration files, overall how the whole system works. Yeah, here you have a recap, a summary of everything, explain it, yes, in a brief way. And yeah, I think we are almost done. We have this Dynamic Reconfigure tool, which is a very interesting tool. Let's have a very quick look here. So until now we have seen how to modify parameters by modify them in the YAML files, yeah, in all these files here, in the parameters files, yes. But we have a tool which is this Dynamic Reconfigure, which we can launch using this command here. And this tool basically what does, this will appear in the graphical interface window, so let's minimize for a moment. Well, actually I think we can already close. Well, I'm not going to close it because I need the move-based node to be running. And here it is, okay. Here is the Dynamic Reconfigure screen. And here, basically, as you can see, you have here the move base. You can click here, And here you have some parameters regarding the move base node that you can tune here, you can modify here in live, yes? So you have some parameters related to the move base node, some here related to the local planner, the DW planner. Here you have them, parameters of the local planner. You can tune them here as you want, yes? Parameters from the Global Costmap as well. There you have them from the Local Costmap also. Here they are, yeah? So here you can basically tune parameters related to your navigation system, yes, in a graphical way and live, yes, without having to modify the file and relaunching everything. Okay, so it's a very interesting tool. You can test it here in this exercise. And here we have other useful visualizations in Rviz. So for instance, the robot footprint. This is not... Okay, there it is. If you zoom, here you have the robot footprint, the footprint of our Husky robot, which is something that can be useful at some point. Also the current goal, which is the current goal that the robot is following. You can also add some displays in order to visualize this to Rviz. Yes. And yeah, that's it. We have finished the chapter. We have finished with path planning. Congratulations. You have finished the navigation course. You have now the project if you want to complete it. And well, I hope you have enjoyed this navigation course. You have liked it. You have learned a lot. This is the most important. And well, I hope to see you in other Robotic Night courses. Goodbye.